Hello. My name's Jackie and I work for Wheatbelt NRM and I'm the project manager of the Catchment Scale Planning in Regenerative Agriculture. And online we also have Amy Ray, who's the project delivery officer, who does most of the legwork for this project, along with our subcontractor from Mulloon Institute. This is a project from State NRM, which is titled Collaborative Catchment Approach to Wheat Belt Regenerative Agricultural Practices. Rather a mouthful, so colloquially we call it the Gabby Koikoi Project, or GQQ for short. The history. Gabby Koikoi has a long history. The group was first established in 1989. It's taken an innovative approach to land care over the past 35 years, and the catchment covers approximately 20,000 hectares. There's all sorts of issues going on in that catchment. They've done a lot of land care work, such as revegetation, refencing. They've done some drainage work, and Lance will address some of the issues that he's been working on in a bit. It's been funded by the State NRM office, and it's to deliver regenerative catchment trial that drives landscape restoration and delivers farm efficiencies to encourage further similar collaborations. And it's a really important aspect of it is that it's to share the information with other catchment regions around the state. Lance works for the Mulloon Institute, which has been subcontracted to deliver the on-farm plans. There are 8 farm plans for the catchment, and this could include revegetation works or earthworks, and in particular using the landscape rehydration techniques from the Mulloon Institute. And without further ado, I'd like to stop sharing and I will hand over to Lance.
Okay, thank you, Jackie. It is a bit slow to respond, so hopefully the slides will catch up to my voice or be relatively corresponding. Yeah, so as a bit of background or context, I guess it's important to just say what is regenerative agriculture, and it's basically the active improvement of the health and function of the landscapes and living systems that it's operating within while producing food. So that's just the definition. Just getting some sound from somewhere. Yeah, so and we're sort of working within that context. So landscape rehydration is a part of regenerative agriculture, and it's quite a critical part because it's restoring the water cycle and building the landscape water function and movement and storage. So it supports regenerative ag and it builds landscape function, in particular the water side of things. So the benefits of drought resilience and extended seasons, increased fire protection and reducing fire impact, managing and restoring saline and waterlogged land, buffering threats and constraints such as acidity, non-wetting soils, toxic metals, etc. Reducing and offsetting carbon emissions through greater carbon storage. There can be a dollar value attributed to that, and increasingly can increase natural capital, which also may attract a dollar value in the future. So why? So our landscapes and energy, water and nutrient cycles that build and maintain them are broken. I guess if you can think of the earth as a human health analogy, the earth has emphysema, ulcerative colitis, which is bowel disease, kidney failure all at once, and maybe even heart disease and various forms of cancer. And you could probably throw in dermatitis for good measure. So not really great health. So the primary root cause is clearing, and that's pretty obvious. You can see from that map very high proportion of land area in the southwest of WA has been cleared from about 1900 to the 1980s. And there's some shires where it's about 99% clearing. So people might have heard of the water cycle, but there's actually two components to the water cycle. There's what happens over the ocean, which is the large water cycle, and what happens over land, which is the small water cycle. So with that removal of vegetation, as you can see, vegetation is key to that small water cycle. So with that removal of that vegetation, we significantly change the small water cycle. And the ways we've done that is increased runoff and infiltration, and we've reduced evapotranspiration, particularly in the summer when we've replaced perennial vegetation with winter pastures and crops. So one of the things we see in that is change in rainfall. So not only is the rainfall changes due to global warming, it's also due partly to that clearing of vegetation. So this is the rainfall from Mulloon Hills, which is just north of the catchment, or the Gabby Koi catchment, I should say. And you can see there, although the total rainfall has only declined slightly over the 110-year record, the winter rainfall has actually declined by a significant amount. So whereas it used to be around 260 millimetres, it's now down around 210. And that's quite important, especially when your major productivity or production activity is winter based, such as pastures and crops. So one of the critical things that plants do is they act as natural air conditioners for the land due to the unique property of water, which absorbs energy when it's transforming from liquid to vapour. So evapotranspiration, which is that transformation, takes heat to the upper atmosphere. And then obviously when the air cools, the water condenses back into clouds and that releases the energy. So it's a really important energy dissipation in our landscape. It also allows that diurnal moderation of climate to allow a little bit of warming at night time as well, particularly in those cold winter nights when you have condensation on leaf surfaces, which then releases some of that energy. So another impact of that clearing is the obvious one, salinity. More importantly, should say secondary salinity, which is the process of salinisation of otherwise fresh landscapes. So clearing reduces the resistance to runoff and decreases soil structure to increase runoff. And also there's less take up by vegetation due to the much shallower rooting of the annual pastures and crops. And less dense roots also increases the deep infiltration. The runoff then accumulates in the very flat areas where it recharges saline water tables, and the salinity waterlogging reduces the soil structure, contaminating soil so it can't store the fresh water as well. Should note that some systems are actually naturally saline, mainly in the northern and eastern wheatbelt and around estuaries, and they're usually detectable by high diversity of plant species, greater cover, but these processes can impact on them as well through further or increasing salinisation. Another thing that clearing does is increasing runoff, which also increases the risk of erosion. So where water is concentrated and we've got high volumes of water that's in those concentrated areas, we increase velocity and the energy of water, which means we can get erosion. And from that, we can lose the chain of ponds effect, which keeps the landscape hydrated. So that chain of ponds is where places in the landscape make water slow and pools and infiltrates. That erosion also allows salt to move down the landscape where it's getting expressed at the surface. the clearing is also exposed soil, which means we've got greater exposure to wind and also sheet and rill erosion. And the worst thing is that when we lose that topsoil, that's the best bit. So it contains the most carbon, the organic matter, and therefore the greatest water holding capacity. And you can see in that bottom right image, that's a crop paddock. So water's been running down the crop lines, down the slope, but also that angled one is a sheep track, and that can be where erosion starts as well. So what do we do in terms of planning? So the first thing is we need to assess what we have, and this is quite a critical step. So I'm going to spend a little bit of time on it. So we'll be obtaining existing information and identifying the features and issues of the catchment. The timing of this assessment is important. So if we're going to look at a site in summer and autumn, we'll see only the perennials, we won't see the annuals, but we will also see it probably in its most vulnerable state. Whereas we go in winter or spring, we'll see all the annuals, but we'll also see where there's wet areas or where the waterlogging is the most severe. So a few tools we use, and I'm going to show you one in particular. So I'll change my screen sharing. And share. Apologies for the delay. So hopefully we can all see that. So that's a tool provided by Department of Primary Resources and Regional Development. It's called NR Info. The link I showed before, the QR code, will give you a link to roughly the Gabby-Goycler catchment. So it's a tool which provides quite a bit of natural resources data that we find useful. So when you first open it up, you'll get a screen that says abide by the privacy, etc. You click on yes and get through that. And then you get this about the data, which will let people go through themselves. One of the...
Sorry, Lance, the link's not showing up.
The one I showed before, the QR code?
No, the screen's not showing up.
Oh, the new screen. What are you seeing?
Lance Mudgway has started sharing a screen. So you might as well just proceed, but just know that we can't see it.
Okay. No, it's a bit hard just without. Hang on. Stop share. We can share it again.
Whoops.
Is that working?
No.
No? What are you seeing still?
Just the black screen.
Okay. What I might do is I'll open this new window.
Okay.
Bear with us. We'll find my bookmark now. Open a new window.
Sorry, everyone.
Share. Not. Okie dokie. Hopefully we can see it this time.
Just waiting because it's been a bit of a lag just to see if anything coming up.
Yeah, yeah.
But
Yeah.
there's nothing coming up.
Slow to load, mate. What are you getting now?
Nothing. So I'll just, what's the website address again for NR Info? It's NR Info. If you search for NR Info to everyone, you should, it will come up and you can explore the tool in your own time. Sorry that it's not working. Do you want to explain what you were explaining, Lance, or does it really need the tool to show? Aha, there it is.
Yeah, it does really need the tool to show. You've got it?
Yes.
All right. So this will probably be a bit slow. Might lag a bit. So I'm just zooming in to the area, and it's slow because I'm on the Zoom as well as using the heavy internet use. It's a pretty simple mapping program, much like Google Earth or Google Maps or Bing Maps or whatever you use. You can use the scroll wheel on now, zoom in, and then just drag and move. So the first thing that shows up is the shire boundaries, which are those yellow dashed lines. So that's Goomalling Shire here, which is where Gabby Koi Koi Catchment is, which I'm going to try and zoom in further to. And up the top right, you'll see a number of different icons, which give you different types of data. So I've just clicked on the layer one, this three little squares above each other, and I'm going to select agricultural properties boundaries. May not show up yet, it's not zoomed in enough. Oh no, there we go. So hopefully you're seeing this.
Yes.
Yep, good. So property boundaries is particularly useful if you just want to find your own property and see what's there for that. Or you can search for a catchment or something. I'm going to turn off the local government and regional development areas. But really what I wanted to show you is some of the other information. So one is the hydrology, which is the water drop. And the two important ones there are hydrographic catchment subcatchments. So they should hopefully appear in a few seconds. There we go. So you can see the Gabby Koi Koi catchment in that purple line based around Conongoring. And the other one is the hydrography linear, which is the rivers and waterways. It generally only shows the major ones. So in this case, it shows the Mortlock River in a blue line, and then that's the Gabby Koi Koi Creek in pale blue, which has appeared. We're also working within the Wallamoring Lake catchment, as the lake down the bottom of the screen. Another important one is topography and elevation. So that's the two triangles on a green blotch. And we'll need to zoom in a bit for this one. One other thing I should add is that if you click on a feature, so hopefully if I click on catchment, you'll get some information about it. Sometimes it picks the wrong one though. I might turn the properties off. There we go. So our catchment there. Just gives us the view accurate table, which will hopefully give you a bit more information. There we go. So for instance, the catchment area is 128.28 square kilometres. And it'll tell you the catchments below it and upstream, and the total catchment upstream as well. But this is the most upstream catchment in this case. Going back to topographic information. We'll turn on the contours 10-metre interval. And this is important because from this we can actually work out the catchment area, which gives us a bit of an idea of risk. So obviously the larger the catchment area, the more flow we're going to get, so the higher risk we're going to have. So in this case, if we're just working in this top part of the catchment, maybe from Mudgway Road, we can work out the catchment area, and there's actually tools. I can map an area and measure an area. So that tool is that little measured ruler below the search bar. I want to do an area in hectares. So we'll start from Mount Joyce Road. I'm going to do this roughly, and then we just take that point. We can use the catchment boundary that's already there. And they'll come down this ridge. So the catchment area at Mount Joyce Road is 1,944 hectares. So that's indicating it's starting to get a little bit risky if we're working down in this bottom part of the creek. And you can save an area as well. One other piece of information that's really useful is on the soil landscape mapping, we select best available. And this gives us a generalized view of the soils and landscape. So if I click on 10-metre contours, let's turn it off. This particular area. So it's in the Wong Hills subsystem, but it gives you a description. This one here is the more important one. I might put that in the attribute table where we can view it. So undulating low hills with granite rock outcrops, grey, brown, shallow and deep loamy duplexes, sandy and loamy earths, and minor of something or other, which you can probably minor of shallow and deep sands, and we've had the vegetation would have been salmon gum, melaleuca, acacia, gimlet, and mallee. So it gives you quite a bit of information about that area, and you can also click on these links and get further information. So the report will give you the percentages of soil types. In fact, I think some of these columns will give that, but this report will do the same. So it'll give you a percentage of those different soil types, which is quite useful. One other thing you can do is, hopefully you're seeing this, and this is actually quite a useful set of data. So it's from data.wa.gov.au, and it's the dikes. Oops. I hope to be able to follow this. There is directions in the fact sheets we'll talk about in a sec. You can actually just copy the URL and you can add data with this little plus map box. And paste in that URL and add. So you can see that's now appearing on our legend, that one there, and it's the green line. So that green line is a dike. And those dikes can be quite influential on subsurface water movement in catchment. So it's quite useful to map where they are and see where that might lead you to go and actually look at those sites on the ground. I'm going to go back to the PowerPoint. All right. So we're back to seeing.
Not yet.
Not yet. Doesn't matter. Another really
Proceed
useful
anyway.
tool. Sorry.
I just said proceed anyway.
Yeah, it'll catch up. I'm just going to quickly go to Google Earth. So Google Earth, we've got some what's happening there. Stop share. Do it again. Yeah, that's weird. I'll skip this one because people can explore it themselves. But in Google Earth or Google Earth Pro, so you can use the version online, or you can use the app version. Really great thing about Google Earth is that it provides a sequence of imagery over time. So you can view various snapshots of time in a map, like the satellite imagery, which can be really useful. Let's go back to our PowerPoint. It actually also has slightly better tools for drawing and measurement than NR Info, because NR Info doesn't let you, if you make a bad point, you can't go back, whereas Google Earth, you can just hit backspace and it deletes the point you've just made.
And your slideshow is showing.
It is showing? Sorry, did you say it is showing?
Yes.
Yeah, good. But the only thing with Google Earth is it doesn't have contours, which is a bad point. But anyway, you can load them in, but you need an app to be able to create the data. Another one is the Bureau of Meteorology climate data. DPIRD also has weather stations, which you can find on their website. So all that data is live. And the Bureau of Meteorology stores all their data, which you can access online as well, and you can click on that QR code and find it. I think the reference is also on the fact sheets. So some of the important information in terms of climate data we'd be looking for is rainfall, and I showed you a record of data before for Wongan Hills. But another important one is the wind speed and direction. So if you click on climate statistics and then select all features, you'll can view the wind roses, what those are called, for the 9 a.m. and 3 p.m. time slots for each month of the year. So I usually just pick January and July, which tend to be the most extreme in winter and summer. And you can see there, this is for Wongan Hills. In summer, the winds tend to be from the east and southeast, particularly in the morning, but in the afternoons it more comes from the south. And then in the winter, the mornings tends to be northerly, but in the afternoons tends to be in the west. So that's very important in terms of wind erosion and for the alignment of vegetation belts to provide shade and shelter. I'm not going to go into detail on this one. The Department of Water and Environmental Regulation has a water information website. Again, allows access to data. The key one for us is groundwater data and surface water quality data. So that can give you an idea of how saline a catchment is, or the extent of salinity within a catchment. So once we've had a look at some of the spatial data and desktop data, it's really important to actually go out on site and get eyes on the ground. And the first thing we probably do is get a historical view from landholders and managers. And we'd be asking questions such as what they've observed over time, what problems and issues that they have, if they've implemented any interventions to address changes or issues, how successful they think they've been, and what are their observations, how do they manage their different operations. So, for example, grazing might be set stocking, cropping it might be no-till. They might use GPS tracking for all their machinery. And it's also important to determine the outlook. So collectively for a catchment, you come together and work out a bit of a vision and objectives for the catchment. So that might require a bit of workshopping. And that needs to include the social and environmental aspect as well as the landscape aspect. And you'd be doing that on an individual level as well as with the group. And obviously individually you'd be looking at what sort of management is going to be going on in the future, whether that's going to be the same or different, what sort of operations and what sort of external constraints might come in. For example, a clear learning one at the moment is carbon and climate change, etc., is having an impact on how we can market things and how we can solve things. So when we're out on the site, our first thing we're looking at is the geography and landscape. So it's important to have a tour with the landholders because they've obviously got, they can provide that history at the same time as showing the different aspects of the landscape. And we're looking for a range of features and characteristics. So slope, landscape slope has an obvious impact on runoff velocity and energy, and therefore the potential for erosion. We're looking for obviously where ridges and valleys and waterways are, and where water moves and where it stops. Importantly, where it stops and maybe where it used to stop but doesn't anymore. And that's what we call the steps, as I mentioned before. We'd also be looking at the types of deposition materials. So alluvial material is sediment deposited by running water in a stream bed, and it can be a little bit confusing because we call alluvial fans, they're actually colluvial, which is sediment deposited by water running over land or down slope creek. And then another feature is aeolian, which is sediment deposited by wind. You'll often see in valley floors there'll be sand dunes or lunettes around lakes and just within the valley floors. They can give you an idea of the material that's within them, and it also gives you an idea of the extent of erosion or historical erosion over long term. We look at the waterways themselves. Are they natural? i.e. a chain of ponds, or are they straightened, deepened channels? In valley floors, we're looking for signs of old waterway channels. We're looking at the bank shapes, dimensions, and the ratio of the width to the depth. So a waterway which is narrow and deep and with steep sides is most likely significantly eroded, probably in the last 100 to 200 years since clearing of the vegetation. Are they meandering or straight? Are they undulating or constant grade? So looking at the sideways profile as in the bottom left image there. And how much vegetation is on them in the banks, on the bed, and in the riparian zone, which is the area either side of the channel. And what's the soil type? Because that can be important as well, because some of our valley floor soils are clays and they're sodic, and sodic soils are very highly prone to erosion. One of the key things we're looking at is the soils and I guess the protection of soils. So there's a landscape function assessment tool which looks at the organisation of the on the soil. So generally applies to cultivated areas. So obviously the cropland is pretty uniform. So we measure the proportion and distribution of covered and bare areas. Where the area is covered, we determine if they're different types. So in this case, we've got two different types, patch 1 and patch 2. One's blue bush and one's a bit of grass. So we determine the surface cover and the perennial vegetation cover and other factors on the different covered and represented bare areas, so the interpatch areas. We'd identify the soil types. So in this case, we've got a gravelly loamy sand, and that's pretty constant through the whole area, that little patch. And the blue bush, it's 100% surface and veg cover. In the patch 2 grass, it's about 90% surface cover and then about 80% veg cover. We've also got a bit of compaction. This area hasn't been raised for a long time or cultivated for a long time. But it's quite compacted. So I've got a penetrometer in about 5 centimetres, which is pretty low. We'd also be looking at if there's any erosion. In this case, there's none. Any animal tracks which can concentrate the flow of water and cause erosion. Any compaction layers. So in the cropped paddock near to this patch of bush, the penetrometer went to about 10 centimetres, but then it roughly went up to 300 pascals pretty quickly. So it's a bit of a hard pan underneath the tilled area, tilled zone. Also, we're looking at non-wetting soils and things like that as well. In this case, this soil is non-wetting. We look at the vegetation from the species and composition of the vegetation. So the bottom image, we've got reasonably healthy Wandoo, York gum, sheoak, jam country, which would indicate the soil type. So that would be a duplex. Well, I know it's gravelly, but loamy to sandy duplex. Top image, obviously a highly modified system, which is now canopod, sandfire shrubland, clearly waterlogged and most likely saline, and clearly modified. There used to be what looks like probably eucalyptus stand in that floodplain, and it probably would have had a grassy and understory underneath as well. And going back to the bottom image, looks very healthy, but there's not a lot of regeneration, which would indicate long-term grazing and little recruitment. We can pull all the information we get together from the site plus the desktop assessment, and we can pull that together in what's called a catchment function analysis. So it gives us an idea of how the catchment would naturally function and where processes and features have been disrupted. So this is the Gabby Koi Koi catchment down to the Mortlock River. The main issue or problem where function has declined is waterlogging and salinity, and that's obviously concentrated mainly in the valley floors and in depressions on the hill slopes. So you can see there's waterlogging extending quite high up into the sides of the hills, and one of the influencing factors is granite outcropping, which is in the sort of dark grey lodges, and quite light soils, which obviously allow more infiltration, concentration of water into the valleys. There are some patches of inundation down the bottom end and some rill erosion occurring in some areas, generally more associated with what used to be gravel pits and things like that. So the next point is just to describe some of the principles we apply to when we're planning in catchments for regen and ag and landscape rehydration. So the key one is to grow more plants. So those provide heaps of ecosystem services and restore natural function. So we want to try and lengthen the time of growing roots in the ground and the green leaf above ground, and preferably we'd want to grow perennial vegetation. And here we often underestimate the value of just single paddock trees as well, providing some of those ecosystem functions like providing organic matter to the soil, shade, stabilisation, habitat for beneficial insect and birds, and there's quite a big list along with that as well, and obviously the microclimate control and the small water cycle restoration. Second one is to protect intact features. So in this case we've got, I don't know whether you can see my mouse, but the area in the top middle is a freshwater source for this landholder, and he relies on that water for all his spraying, stock water, and everything, so it's quite critical. But you can see this creek line is definitely waterlogged, and further down the system is saline, and that salt and waterlogging is rapidly working its way up the system. So it's actually threatening that freshwater source. So we'd want to try and protect that freshwater source through doing various works, which we'll go into in a few minutes. Another thing we apply is to halt active erosion and salinity. So we've got, obviously, again, salt in the valley floor down the bottom of the image, and that's creeping up into an area that's obviously being cropped, this area here, and still cropped further up. So if we can halt that salinity, obviously that's going to protect the area that's still croppable, and hopefully also make this area more productive in some way. And as in the previous slide as well, so halting that active erosion and salinity will actually help protect that intact feature. Critical one is keeping fresh water fresh. So we want to try and bank water higher in the landscape where it can be used. and reduce the main drivers of salinity, which I described before, which is that runoff, excess runoff, landing in the valley floor and causing recharge. So the top image, we've got, this is quite high on the landscape in the Gabby Koi Koi. So we've got waterlogging, but the water's fresh. But that's water eventually makes its way into the Gabby Koi Koi Creek, which is the lower image, which is the floodplain of that, which is, as you can see with the sandfire, is quite saline. So if we can keep it up where that waterlogging is, we can use that water while it's fresh instead of just basically to be wasted in that saline area. A couple of other principles, we try and build healthy soil. And one concept I want to introduce here is positive feedback loops. So a positive feedback loop is where something happens and it, that reinforces the behaviour. So in some cases it makes it better, in some cases it makes it worse. So in terms of building soil, this can be a positive feedback loop in a positive direction. So the key requirements are water and organic matter. So the organic matter can come from plants and animals. And yeah, so once you've got those, plants will grow, fungi and microbes will grow, and then that provides more organic matter, which then allows greater capacity to hold water, which then grows more plants and more fungi. So it's a building process. So our intention is to support these positive feedback loops in positive direction and flip the ones that are going in a negative direction, for example, erosion or salinisation, into a positive direction. So they become a building or a restoring system. So we provide a foundation for nature to create those positive feedback loops in a positive direction. Quite a simple one. Don't burn your moisture or organic matter. That's just a stubble burning fire. You can see the moisture that's been lost from the stubble forming in clouds above the smoke, and obviously that smoke's containing carbon and organic matter that's been burnt off, and then that obviously won't feed your soil. Another important one, slow the flow. So we want to try and reduce hydrograph height, hydrograph being flow over time, as well as the total volume, and extend the time over which it occurs. And that allows water to infiltrate higher in the landscape and also reduces erosion. So just a little bit about erosion. So it's a result of the power of water under influence of gravity. The key parameter to reduce energy of flow is velocity and depth, which is related to the slope and surface roughness. So we can reduce the slope by stepping water down a slope or by increasing the length of flow. We can increase the roughness by reducing the depth of the water and or increasing the surface cover. And we can reduce the depth by spreading water out over a wider area. One other thing we try and do is just imitate nature. So nature actually forms its own steps by itself. And this is just an example on a access track next to the railway line where debris forms on a contour that slows water, that deposits seeds. You can see yucca grass growing in that contour from previous occurrences of this contour. So we try and recreate these steps in the landscape. And another one is division of the landscape into 3 zones. So the top is an accumulation zone. So it's accumulating nutrients, water, and provides that natural climate control that plants do. And you've got your majority of the area of the agriculture zone. And then down the bottom you have a filtration and recovery zone. So you can replicate these zones multiple times down a slope, depending on your operation and how you work. And you can use animals to actually cycle the nutrients from the filtration zone up to the accumulation zone, the recharge zones that's described up there. So some objectives. In the valley floors, we're at saline. What do we want to do? Well, we need to lower water tables, and that's critical, ideally by vegetative means. And this is an aside, I've rarely seen deep drains that are very effective, and pumping, although effective, is very expensive. And then with both of those, you've got the transfer of the problem downstream through highly saline and sometimes even acidic water, which is then depositing on someone else. It's important to reduce evaporation. This can also be done by vegetation, but also through mulching. So that example there in the lower images is an area that was quite saline, as you can see from the sample. He had some old barley seed with weevils in it, so he just spread that in a windrow. And those images are from 5 years later, so it's maintained a new ecosystem on those windrows. We'd want to reduce the runoff into the valley floor, so we're directly reducing that recharge, which is raising the water tables. And once we do lower the water table to, well, in a clay soil less than 2 metres, the salt will stay below the surface and provides a space for fresh water to be stored in the soil, which restores the natural function. Where there's saline inflows that we can't manage by reduction of runoff and managing saline areas upstream, then we may need to convey that saline water slowly through the landscape to prevent inundation and further recharge. And that's obviously where catchment scale management is very important, because if we can get that whole catchment view and action, then obviously there's less need for doing those surface water conveyances. You may still want to do it in the short term, but ultimately you'd probably look at other measures which would then mean that those conveyances not required. Hill slope waterlogging and salinity, which is quite common even in the fairly shallow slopes or slight slopes in the Wheatbelt. Critical objectives is to increase evapotranspiration and restore the water balance, and that's mainly on those areas themselves. We also want to divert, and we use plants generally for that, hopefully perennial. We'd want to divert water away, so keeping fresh water fresh and putting that onto the dry areas where it can be used. These areas are likely to have erosion, so it's important to monitor that and address it where we need to. And I'll describe some tools for that in a few minutes. Sheet and will erosion and wind erosion exposure. So soil cover is critical. Mulching is a useful tool, and that image on the left is just hay spread out on a relatively bare area, which is a result of groundwater seepage. So ultimately we want that cover to be provided by vegetation and litter. We don't want to prevent runoff into the rills or exposed soil. So that left image again, you can see the top right, sorry, there's a contour. You can also see there's some lines there, which is some revegetation work as well. In terms of wind, the image on the right, there's a planting that's right along the ridge, and that's due north-south, so it's against the prevailing easterly winds in summer and westerly winds in winter. So basically providing shelter for the paddocks either side, and also shelter for animals in those paddocks. Where waterways are incised, we've applied similar sort of concept. So we want to slow the flow and allow sediment to deposit into the gully and stabilise those gullies with vegetation and other rough materials. In the top image on the right, there's a fallen branch there which is already helping to do that. Obviously in a fresh landscape we can do pretty much what we want. We can plug that creek to actually allow water to spill back out onto the floodplain because the water's fresh. But in saline landscapes, we don't want to pull water for too long, spread it extensively. So we might use structures that are quite a bit more leaky, that slow the flow, but not hold it up for long periods of time. However, it is worth considering that in larger flows, even on a saline system, the flows are likely to be relatively fresh. So it might be worth having those spread to flush the system and provide banking of water, fresh water. So in that lower example, we've got a gully with head cuts, which actually drains the area, but it also provides a greater surface to express the salt, and also removes soil that could be used to grow stuff and also store water, and reduces the scope for fresh water to spread. So various tools we can use. There's various management things which are quite simple, well, sometimes quite simple. Mulching, as I've described before, using hay, straw, any agricultural refuse in areas where we're hoping to get maybe production off, so maybe introducing pastures, for example. But where we're not proposing productive use, then maybe brush with seeds in it can be used as a mulching material. In that image, we've also got contours and revegetation, so things being used in combination. Cropping on or near the contour reduces the run and steepness of rills in the soil. Using straight disc no-till eliminates the rills which channel water, so we're taking a step further. Again, obviously on the contour preferably. Grazing management, so what's used to be commonly called cell or rotational grazing is short, intense grazing with a long period for recovery, increases overall pasture growth, increases the presence of desirable species, and increases soil cover. So all good things. Native revegetation, can't go past this one. You get multiple functions out of it, all those natural functions that vegetation provides, especially perennial vegetation. Need to obviously take into consideration fencing and grazing management. We don't advocate that you lock them up completely. You would still use them occasionally to graze in, and sometimes they can be very useful, autumn break or shelter paddocks. Fire management is another one that's important to consider, and that can be in remnant vegetation as well as revegetation. Excuse me. And then different forms, so windbreaks, shelter belts, water balance plantings, riparian plantings, provide filtration stabilisation, and there's a huge more range of ways we can do native vegetation. Perennial pastures and fodders are important, particularly on otherwise unproductive saline or waterlogged country. There's various species around. Some are also drought tolerant, for example, saltbush. And there's quite a bit of ongoing research and development of new species. So it's worth checking out on the DFID website what's information available about new species. And the fact sheets also provide some links to some known species at the moment. And they can be integrated with cropping as well. Quite an important one, contours. So this is really about that diverting runoff and dispersing runoff back into the drier areas. So they're cut to above the heavier subsoil to allow infiltration. In this case, the subsoil is quite deep. So those ones were 300 mil deep, but often they'll only be 200 or maybe even only 150 mil deep. They're on a contour because they aim to disperse the water and not to flow water fast or anything. And often you can place on a hill slope waterway to redirect runoff away from the valley floor. Just a few more images. Couple other aspects of the contours is that we put in primary sills on the ridge lines to allow medium vents to disperse and spread out. So that's primary sill there. Not sure if you can see my mouse pointer. And then secondary sills at points of concentrated runoff. They're set higher to allow larger flows to overflow and not damage the contour banks. There we go. And they can be done in combination. So here we've got a contour bank, revegetation above a saline or brackish seep with some erosion scalding, and just revegetation using a tree planter. And then this is the same, that's that tree line with the windbreak that I showed before. So you can see there's integrated plantings all the way across the ridge, providing that accumulation zone, and then also buffering native remnant vegetation. There are other forms of contours. So this one's just a simple rip line on a scalded area, which had sheet erosion, but it was used to provide roughness to trap sediment and seed, as well as some water. And that top image, the left image, is 6 months after the ripping, and the first bottom right image is straight after. And you could also use hay or lay out roll of hay on contour as well, as a simple contour as well. In-stream structures, I'm not going to go into a great amount of detail. There's 3 types: flow around, which is generally earth, flow over, which is generally log and rock, and flow through, which is brush. They're fairly self-explanatory. Flow around, water goes around the edges, so it's actually put out onto the floodplain. Flow over, water goes over the top, so they need to be armoured, and flow through, basically the water flows through. So we've got a couple of examples there. Left is a flow through. Top right is a flow over rocks, and bottom right is a flow through brush held up against a couple of stakes. So we can use them to plug gullies, to build the channel back up, to allow water to flood back out over the floodplain, obviously not in saline environments. We use them to slow the flow and raise water levels in the creek line, again, generally not in saline areas. So where do we start? Generally the top of the catchment, because we want to reduce the runoff in waterways, which reduces the scale of intervention downstream, and also follows the important principle of keeping fresh water fresh. Obviously we want to factor in priority issues, for example, maybe rapidly expanding waterlogging or salinity, like that one I showed earlier, where we need to halt that quickly as a first priority. In terms of design, in-stream works we usually design from the bottom of the reach up, from a safe point where there's stationary water or slow flowing water, so that the last structure is protected. We generally, particularly for larger projects, we stage the project to allow time for delivery of materials and bad seasons and all that sort of stuff. And that also allows time to monitor and evaluate as we go, and that then allows adjustment to the plan if necessary. And obviously also there's practicalities such as availability of contractors or earthworks machinery. And the other thing is you might want to implement something like earthworks in one hit to avoid multiple mobilisation costs. And obviously weather is another important consideration. Last part of the sequence is monitoring. So once we've done some work, we want to see what's working, what could be improved. A few useful tools. Photo points, really simple, very just obvious. You just show someone 2 photos like those 2 at the bottom, and you can see change. It's important to repeat the photos at similar time of day and similar weather conditions and same orientation, so use landscape or portrait or And as easy setup with just having 2 stakes in the ground. One of them could be a fence post that's already there. Aerial imagery. If you've got access to a drone, fabulous tool, not only for monitoring but also for just getting a different perspective when you're doing a site assessment. And you can map an area multiple times and measure the actual area of whatever it is. So in this case, it's a waterlogged, somewhat saline, shallow depression. So we can track whether that's increasing or decreasing in response to whatever we're doing. If you don't have access to a drone, then that Google Earth imagery can be useful, as I described earlier. Soil measurements, you can do a simple infiltration test, just banging a ring into the soil, adding the same amount of water and measuring how much time it takes to infiltrate the soil, and repeating that. So if we're doing regen and landscape rehydration, we would hope that the infiltration rates are increasing. Compaction, so you can just use a simple spike. If you've got access to one, a penetrometer, which actually measures the pressure as you drive the spike down by hand. Just digging a hole and getting the soil depth, particularly the topsoil depth. If we're building soil, then that topsoil depth should actually be increasing. And you can usually tell that by the darker colour by the presence of organic matter. And you can do chemical and biological analysis. So most farmers will already be doing chemical analysis through their soil testing. You can add biological as well. You can measure vegetation. Simple measures is just the cover, and that's just a scale that most ag organisations use. And that's just a simple quadrat, and you by eye measure the cover, and you can also do the same thing and look at the species diversity. So lots of species are living in that patch. You can go take a step further and actually cut and weigh and measure the biomass. But there are other methods to do that as well, which we'll go into in a sec. And it's important to also measure production values such as grain yield, pasture yield, animal carrying capacity, things like that. And lastly, as we're aiming to lower salinity in the surface water, we want to measure the surface water salinity. Fortunately, it's not something you have to preserve the sample. So if you don't have a salinity meter, you just grab a sample, take it into your local land care office or deep herd office, and they should be able to measure it for you. And lastly, we're aiming to lower water tables. So if you've got any observation boards in the area, measuring the water table depth is useful to indicate that response. And that's it from me. I'll stop.
Thank you, Lance. Has anybody got any questions? We're pretty much out of time. So what I might suggest is that you type them into the chat. I'll leave it open for a few minutes. And we can go from there. Or you can email your questions to info@wheatbeltnrm.org.au. And then if you've got any questions, you can send them in and I'll forward them to Lance, and then we will send them back out to you. Oh, someone's written, where would you take a biological test, in the gully or in the paddock?
Depends on what you want to evaluate. So you could probably more so in the paddock, because you want to see what your biological response is in your pasture or your cropping or whatever you're doing.
Okay, thank you.
Thanks, Lance.
And response to Don's question early on about missed raindrop nucleation. There's lots of things I didn't say because I didn't have enough time.
Thank you, Lance. And thank you everyone for attending.